a tone appears, then hides. Each sound checks itself before speaking. Harmony is
Okay. Hello everyone. I welcome you all to the sponsor presentations. We now have Pankaj from Qualcomm. It's okay. Yeah. Okay. Hello everyone. I welcome you all to the Hello everyone. I now welcome you all to the sponsor presentations. We'll start with the first presentation by Pankaj from Qualcomm. Hello everyone. I now welcome you all to the sponsor presentations. We'll start with the first presentation by Pankaj from Qualcomm.
Okay, we use the speaker. Yeah. Yeah, hi everyone. Think very sparse audience, but that's fine. It's the conclusion of like the second day. But I think we have the hackathon, so I think more people would be interested in that. Um, so this particular conference has been interesting for me, and I think for Qualcomm also it was slightly interesting, I would say, because we had around like 5 speakers, I would say, including one poster, and this is the best our team uh, could represent at any conference. So it's a big thing for us. I think, I don't know if everybody got a chance to see the presentations on RISC-V. We had one on ELD, one on the plugins, and there was one on the vectorizer also, uh, the poly work which we have done. So I think what I would say is we have covered almost most of the projects on which we work at Qualcomm. The two things which like we were not able to present is what I would cover here. So, and that is the most interesting one, I would say. So the interesting one is the hexagon and the NPU. So they used to call it DSP with when the same DSP gets used for different workloads, the name changes. So that's the NPU. So I'll talk slightly about that, and I'll try to also introduce what kind of MLIR work we are doing for this particular NPU. So, so far I think we have had a lot of presentations on MLIR. I need not go into what it is. Everybody understands what MLIR is. So there is a challenge for us when it comes to running this models on NPU. So before I go to that, maybe I'll ask a question. If has anybody earlier heard about hexagon NPU? Anybody know? Okay, good. At least 3, 4 hands, so that's okay. Thank you. And do you know there is something called as Qualcomm GitHub where some models are hosted and you can run them on the, you can rent the devices and run on that. If any, does anybody know that? I was expecting zero, so that's that's expected. So because that is the work is still under progress. So I think what happened as Qualcomm over the 2 years, like I have been witness to that, is they have moved away from being a downstream only company to like giving access to people so that their hardwares can be programmed. So that's one different approach which has happened, and mostly we have been speaking about hexagon, how you can program or not. It's actually difficult to program it. So I was talking to one student from Triple IT Hyderabad, and he has been able to, he's now working in some other company. He has been able to program hexagon with just the online documentation. It's a big thing. So, and it's a big thing not for people outside. it was pleasantly surprising for us also that how somebody can do that. So, and don't want that kind of experience. So that's something we want to change, and it's a progressive step. We are going slowly. So to summarize, the compiler team for which I work on, it caters to multiple architectures. For example, so we work for microcontrollers, we work for this DSP, we work on the ARM CPU also, and we have also one MLI team, so which I will talk about right now. So the challenges are interesting. I liked it, so that's why I'm there in that team. So and we get exposed. It's a closed team, around like 30 engineers. So we get exposed to all the other compilers also. So if when let's say I'm working on RISC-V, it's not like I don't know about what's happening in this MLIR, or I don't know what's happening, what's happening in the ARM world. So I get exposure. Our folks also get exposure to that. So so that's a good part. So going to one use case, I would like to share a recent one. So did anybody watch Avengers Infinity War, the scene where Tony Stark says, calls Friday and tries to get some information? I hope everybody should have watched it. It's an iconic movie. So just think, you did watch. So what's interesting about that is, in cinema, what ideas can come. So if I look at that as an engineer, for me the idea is about the glass, how you can do it with the glass. So that was very interesting thought, that will it come in real life? And recently, if you would have seen the news, there is the smart glasses by popular company that has the Qualcomm chipset AR Gen 1. I was surprised, amused, and I saw multiple articles, and everyone was like, what? This is a nice thing. So what was nice in that was, you are not running the models on the cloud and getting the information. You are running it on the device, on the edge. So is it really possible? They made it possible, of course. So what kind of models are run on that? So then we have to understand what use case is also there on the glasses. So what you will say on the glasses is, okay, whoever is the speaker, just show me his profile. So then you will need that lens, maybe kind of a binocular lens, where you can see the, let's say Pankaj Gode is there, what all he has done since how many years he has been working, all that you can see. So you need that lens. You need, maybe you need something to, some kind of device or some interface which reads that for you also. So you will say, okay, read that for me. So now I think you are understanding what is happening. You are giving it a command, and it's translating it on the fly to give you the data. So that's an interesting use case. By the way, this particular work which I'm talking about is still under development. So it's not used in that particular project. So there is a Hexagon SDK which is used for doing inference on the glasses. So that's a different thing. But this is something which is under development. Generally, like we see companies talking, and they will say, oh, this is under development and I don't want to reveal that. We are like, okay, this is under development. Get some ideas. If you have something, please let us know if you can solve it in some different way. So in this case, our problem statement is to develop this open source compiler for ML applications, of course, for NSP. The challenge here for NSP is, if you see all the models, everybody has talked in these 2 days focusing on GPU. What if you want to run the models not on the GPU, on this kind of device? So what is the challenge with this device? So the challenge with this device is power efficiency. You want it to be very power efficient. Because on the glasses, you don't want it to heat and your brain to fry up, right? You want it to be very power efficient. You can get your data. So again, I don't think you would have read, but on the glasses, the model which is run is the small language model. I wanted to know what kind of small language model it's running, and I was surprised it's running Llama 3.2, 1 billion parameters. I was what? Llama 3.2 with 1 billion parameters? Awesome. On NSP. It's a good thing. So, means what I want to say is like the NSP has become efficient to run such models also, where you can do that image processing on the glasses. So the challenges which we have here are this block diagram. If you see, is this is not available much online. So this, but you can derive it. It's not a big thing. So interesting part here is if you see there is a scalar processor, there is a vector unit for vector operations, then there is a tensor unit, and you have memory processing also. Now these components all are dependent on the VTCM, how efficiently you use VTCM. So if you see, this is a shared memory between vector unit and tensor unit. So if you use it efficiently, then yes, you are doing a very good job. If you are not doing it, then there is a problem. Your power efficiency goes away. So this is one of the problem we are looking to solve when we are trying to develop this compiler for ML applications on NSP. So the engine, the overall Qualcomm engine, AI engine, which we call, so that has, I don't think this diagram is much visible, but I'll just spell it out. So you have the NPU, you have the GPU also, of course you need that. You have the CPU, and you have a sensing hub. So all these are required for doing any kind of inference on the edge. So here again, as I was saying, the challenge is NPU and how you program the HPX. This is slightly difficult right now. We are working towards making it easily programmable. So this is the target hardware for which this particular problem we want to solve. Now, MLIR is, I think, something we have, I was saying, like we have been hearing about it from everybody. What we are interested here is the DMA generation, the memory management, the vectorization. That's of interest for the NPU world because of this shared memory architecture, right, which I was sharing about. The VTSM is limited, it's fast, it's shared. So that's the challenge we are looking to solve. So how do we solve that? This again, I think this is we all know. It's like about dynamic shapes, sparsity, all that problems everybody knows. So this is the AI stack which again we are all familiar with. So there are three areas where we want the AI workloads to, three areas we should address in order to support AI workload to run on NSP. So one is doing the core MLIR development. So what we want to do in this is we want to develop some kind of dialect. Dialect, I think, is now very native to India because every 100 kilometers we have a different dialect. So not surprising that we end up creating so many dialects. So in this case now we are creating a hexagon dialect. Then we would also be creating a Triton MLIR development workflow. And finally, the overall torch MLIR development, where you have a torch model and it goes through the full flow. So this is the high-level flow we would be looking at. So when we want to support Triton workflow, so you have a Triton custom kernel. It can be optimized, it may not be optimized. It gets converted to a Triton dialect. And we are not directly converting from Triton dialect to a hexagon dialect or a custom backend dialect. We want to leverage on the lineage dialect. The reason is it offers your tiling, fusion. Those are very important for the hexagon dialect. So that's why we had to introduce this in the workflow so that the hexagon dialect gets benefited. So this is a typical four-step flow. You have Triton dialect, lineage dialect, then the hexagon dialect, then the LLVM dialect, which then runs on the LLVM hexagon compiler, goes on to run on the NPU. The binaries goes on to run on the NPU. So this is the flow we are targeting for Triton. Now currently what we are trying to do is we are trying to develop this hexagon dialect, where again the challenges are similar. Like addressing the multi-core, multi-threaded parallelism, vectorization, how you can map your workload to tensor unit. That's also one area we are looking to solve with this hexagon dialect. It's a challenging area because I was saying, right, there is a VTCM which is shared between both tensor unit and the vector unit. So we have to map the workload such that you get the most efficiency. So when this slide was made, so we were looking at hexagon dialect, but now we also have introduced something called as a hexagon memory dialect, which takes care of DMA operations, transferring data from VTCM to DDR. So those operations are included in the hexagon dialect. This is still under development. As I was saying, this whole project is under development. So anything you want, you think might be interesting, you can talk to us, maybe contribute some way. I think soon this work will be upstream. So then the final part is running the overall PyTorch model, supporting the PyTorch workflow, wherein you have your PyTorch model going through the full flow of getting Triton kernels in Triton, which you can go through the flow which I had explained earlier about like uh, going through the Triton dialect, the Linux dialect, and the hexagon dialect, and making it run on the hexagon NPM. So this is the work which it's under development. So if you have any questions or doubts about it, please reach out. It would be nice interacting and getting to see if we are missing out on some obvious things. But here, as I was saying, the challenge is managing the memory between the tensor unit and the vector unit. So that's all I had. Thank you very much.
Thank you, Pankaj. We now have Samira with us. Samira from Quadric. Sorry. Okay. Okay. Oh yeah, I'll have to play. Okay. Okay, perfect. Thank you so much. I can do it from here as well, right? Okay, perfect. Yeah, thank you. Hi, good afternoon. I'm Samira Deshpande, Principal Software Engineer at Quadric INC. We are pleased to be sponsor at ISCT this year and hope you all enjoyed last 2 days of the conference. Uh, Quadric is uh, a developer and licensor of unique domain-specific processor. So we do not really build the chip, but we license our IP, and we are pure play semiconductor IP licensing aimed at AI inferencing. So this
we are based in Silicon Valley. Office is in Burlingame, California. Um, and this is the first chip that we built as a prototype, but we no longer build a chip. So we like to just show this chip because this is the first time we had a POC that this concept actually works. Um, we license our Chimera GPNPU, which is General Purpose Neural Processing Unit, to wide range of silicon design teams around the world. And because our customers are in diverse range of applications, we have different chipsets to cater to their needs. So for example, Nano is for 1 to 7 AI tops, then P, which is Perform for 4 to 28 AI tops, Ultra is for 16 to 108, and then we have Multi, which can go up to 800 teraflops. So this is NPU for us. Um, so yeah, because we have, what has happened? Ah, okay. So because of these wide ranging applications, we have different variations in the architecture, but overall the architecture layout is pretty same for us. So let's start with the most important part for any NPU, which is the MAC unit and then some local memory, right? So that is MAX and LRM for us. Then to add to that, we also have a register file where local computations can happen, and then some 32-bit ALU operations which we can perform in parallel to MAX. Then in addition to that, our processing element, so this is called as a processing element. Each processing element is connected with its neighbors. So there is a neighbor axis, and then there is a DMA control provided to this. And then there is a, if you look at the instruction, it is combination of compute instruction and data movement instruction. So we can, single instruction can initiate a compute operation as well as data movement operation. So now this is our PE, and it sits in, yeah, so this PE sits in array of processors that we have, and depending upon how many, what is the size of this array of processors, so depending upon size of or dimensions of this array of processors, we have the configuration of N, P, U and all, right? So now this is our whole architecture. We call it Chimera because you can use the architecture for, so different parts of the architecture is capable of doing different things, and so it is Chimera GPNPU. So if you see here, we have a single instruction. So we have a single instruction port, then there is a data movement. You can notice that there is a local memory which we call LRM, which is sitting in each PE. In addition to that, there is a on-chip L2 memory, and then there is an external connection to the external memory. So there is a hierarchy of memories that we have, and that poses another level of problems for the compiler. So yeah, we are scalable from 1 TOPS to 860 TOPS depending upon how many Ps we have and how many such cores we have in the multi-core processor. So to exploit power of our architecture, um, we need the best compiler to support our architecture, and this is how we have implemented our compiler stack. So the Chimera graph compiler is at heart of our the compiler stack. So the CGC takes input from either the PyTorch in form of Onyx, or from the ChIPy compiler, which can again generate a relay input for us. Then the Chimera graph compiler generates C++ code. Then the users can also write custom operators or DSP application code, and some function libraries are there. So all can be compiled using Chimera LLVM compiler. And then we have a Chimera ISS, where our code can be seen running, or we can have a target silicon with Chimera GPNPU, sorry. Um, because Chimera graph compiler is at heart of our software stack, I'd like to talk more about the graph compiler. So yeah, so we take Onyx as input, then we have some, we do some graph analysis on the input, some graph simplification and canonicalization, and then some local optimizations like graph propagation on it. Then there comes the actual graph optimizations, which are very target specific for us, right? So there is some requantization or requantization and rescheduling happening. Parallel graph serialization happens, and then we can fuse some of the operators and select the implementations to minimize the data movement cost. In such architectures and such applications, data movement cost is far more than the compute cost, and so these optimizations play crucial role in generating the optimal code. Then because we have multiple layers, 3 layers of memories, the memory optimization becomes quite important for us. So we have to pay attention to the tensor format layout analysis, and then intelligent weight prefetching, for example. We have to do that to optimize on the time taken by the data transfer. So this is CGC's high-level architecture. We use TVM project as a base for our CGC. And then we have architecture-aware quadric-specific middle end, and then there is a direct mapping from the EPU relay, that is our architecture's relay code, into the TIR generation, which finally generates the C++ code for us. So to see what we were able to achieve, this is what we have already supported in our CGC. So you can see there are 74 ops from Onyx that we have already supported. We have added few algorithms in SDK so that that support is there. So you can see that even though our hardware does not need to change, if new algorithm comes in, or if new feature is added, or new neural network comes, we just have to add a support in the software in any layers of this to actually get the implementation and things running for us. So if you have any questions, if you want to know more about what we do at Quadric, please reach out to me. So these are the planned optimizations, but because short of time, I cannot go over that. Please reach out to us if you want to know more about us. Visit our website. Thank you.
Thank you, Samira. I thank all our sponsors. And with that, I hand over to Ashutosh for another interesting session on hackathon presentations.
Thank you so much. We'll be beginning with the hackathon presentations. All the teams who are presenting today, please come and be seated in the front row. And I also request the judges, Uday sir, Casey sir, and yeah, sir, to please come forward and be present. So up first is team We Don't Know LLVM. Please come on to the stage and get ready to present. So just explaining the format, each team has 6 minutes sharp to present. At 6 minutes, you will stop presenting, and the rest 4 minutes are reserved for Q&A.
Then I need only HDMI. HDMI will work only. The USB you want? What? Well, I don't know. I haven't tested it. So what do you mean? So what? Wait, it's connecting. Okay, did connect, but why? Okay, yeah. No, you just mirror the screen. Yeah. No, I'll just mirror the screen to the other side. Okay. Oh wait, you have Linux? Yeah. Okay, then display. Just go to display and then mirror. Wait, simple loop. Like just I just increase the brightness. Just copy the screen and put it over there. Can we do that? Yeah, we can. Head over. There's a slide here. Oh. Just 1 second. 1 second. Just 1 second. Yes. Yep. Okay, I'll share it. Do you need link with you? Just tell me. Just don't share it on here. Just tell me. OPU hyphen. This thing from KRZ OHS. Yes. Fine. You join and share your screen over there. Yeah, just join. We look express stage apart. Yes, sir. Yeah. Then come. Just share your screen over there. You have internet? Yeah, I do. ये बोल दिया we verified 1 month वाला. I mean, I do have internet. The site opened. The stuff is running. Ratsa, okay, Nissan. Well, I don't have that much bandwidth. I'll be using internet during the demonstration. You don't have internet? I do, but I don't have that much bandwidth. Yeah, it's fine. We'll keep that included, yeah. So we'll go to source. Yeah, just switch this and then press on slicer. Well, I'm not speaking. Okay, you can. I'll be speaking. So just 1 second. So yeah, I guess it works. You can turn this off. It's fine. So okay, we start. Hi, we are Pragyansh and Varun from team We Don't Know LLVM, and we present Python BPF, a Pythonic front-end to write BPF programs. A quick primer on what is BPF, a kernel subsystem which allows custom programs to run in the kernel space, provided they conform by the rules of the BPF verifier. This is helpful in networking, monitoring, kernel bypasses, and observability. One more. So we'll focus on BCC, which allows you to write BPF programs in Python. And there is a big problem with BCC. It's inline C in Python. And if we take a closer look at the syntax, we see more than half of the file is C of this basic example, which can't take advantage of a Python LSP and the linters. Also, this is objectively ugly. And this leads us to our problem statement. Make a truly Pythonic front-end for BPF programs. It will be easier to learn and can take advantage of the Python ecosystem. Next. Next. And this is a side-by-side view of the same function. Left is Python BPF and right is BCC. You can see the difference is night and day. We get an easy-to-learn, truly Pythonic way of writing eBPF, which can utilize the Python ecosystem to enhance developer experience and data processing and visualization. And why did we choose Python over designing a new DSL? Because everyone already knows how to write Python. All BPF logic is written in functions decorated by a BPF decorator. We support pointer, integer, and string types and try to convert them to desired types when passing them as an argument to BPF helper functions. Next. And under the hood, we translate pure Python to an AST using Python's AST module, so we don't need to write a parser. We check for the decorator function, lower those chunks to LLVM-IR using Numba's LLVM Lite project, and then use LLVM backend to lower it to eBPF bytecode. And how did we design our syntax? We took the BCC examples, then we converted those programs to reduced C, and tried to write them semantically in Python and created a Pythonic syntax for that. So a reduced Python used to write BPF programs. In the same file, we can write pure Python as well. And next. We'll skip over this. These are fine-grained. No, here. Right now, these were some to-dos we decided to do during our first eval on 14 September, and we are happy to tell that we achieved them. And we are still a long way off, because we need to use the vmlinux.c generated from target machine to access kernel structs and kprobes. What's happening? Okay, next. You can try it out yourself. It's open on PyPy, and we are open to feedback and bug reports. And we'll talk about some of the traction this project got. We reached 130 GitHub stars within the first 3 weeks of the opening commit. And one of us blogged about this on our personal website, and that attracted some attention on Hacker News, Python Weekly. Isovalent gave us a shout out. We were reached out by many engineers working on BPF to give their review and discuss future direction of the project. We plan to refactor it, remove the ugly bits, and make it production ready. And now we'll move to the demos, because we planned for 7. Yep. So the first one is an express data path, not the hello world, express data path. Express data path example, it's an example with 3 sub-examples where we first send packets to a network network interface. It will read it, increment a counter, and then send an ACK back to the source. And in the next example, it will accept a network packet, increase the counter, but not send an ACK back using XTP drop. And in the third example, it will only send ACKs back for the first 10 packets, and then it will start dropping packets. So we'll run these examples one by one. So for the pass-through, first example, and then we ping another computer at our home, connected on the Tailscale network, ping a home node. So you can see the ping packets are going back and forth. On our computer, we can see the BPF count, BPF program increasing the counter, and the ACKs are also going back. We have a good amount of packets sent. Now, the packet drop example, if we ping our home node again, and we wait for some time, yep. So now we can see that the packets are being registered here, but we are not sending ACKs back to the home node. So on the home node side, those packets are being seen as dropped. So if we stop it now, we see 100% packet loss because the packets will be being dropped. And in the third example, you'll see the packets go till the 10th count, 11th count, and then start getting dropped. So yeah. Please. Yup. So you can see the counts increasing on our side, but we have stopped sending ACKs back. This was all in Python. Next, we have an example of matplotlib being used with Python BPF, where we are tracking all the number of clone syscalls made within a session of 10 seconds by different processes, and create a frequency graph where we show the number of processes which issue X number of clone syscalls. So right now we'll open some terminals to simulate, stimulate those syscalls. And you can see the number of processes, and there are a lot of processes, more than 500 doing 1 or 2 clone calls. But at the end of the right end of the graph, you can see some processes doing an unusually high number of clones. And we believe that it would be the number of the new terminals we opened, because that was the only significant thing we did in the last 10 seconds. And we opened 5 terminals, so it's kind of there. What? Yeah. 5 anomalous PIDs found with more than 40 clones. If we redo it with a different number of terminals, so like if we restart the whole thing, yep, stop.
You can take 10-15 seconds.
Yeah, we'll just do it again. So. And we do it a different number of times now. And then the last cell, this time it was 7 windows. So yeah, we have found the culprit of that. The culprit was the terminal process issuing an anomalous number of PIDs. There are more demos where you can visualize PIDs issuing a number of open access calls and things, but we'll just do it. We are open to questions now.
Okay, so that concludes your time. Questions?
So one of the important considerations for anything to do with kernel is the efficiency. So how does the time of, how does the code that you generate with this compare with the code that used to be generated with the earlier ePBF notation? Yeah.
Right. So here are 2 things. First is that eBPF code, the eBPF bytecode generated, does not account for a lot of performance hits by itself, because those programs are very small and don't take a lot of CPU time. Also, the most of the performance bottleneck in all of these things is reading things from kernel maps, I/O, and sending data from kernel space to user space. That's the biggest bottleneck. For that, we are using Python bindings for libbpf. And libbpf is the way of doing this using C as well. So that bottleneck stays the same as in C. And for our BPF generated code, what we are doing is generate LLVM IR and let LLVM backend do the heavy lifting of optimizing things to BPF bytecode. And then kernel has a JIT compiler for different backend architectures like ARM, x86. So BPF to the final thing that runs on the kernel VM is done by kernel developers themselves. We asked about this from some kernel maintainers, that should we actually think about efficiency in our case? They were like, no, that's the job of the LLVM project and the Linux kernel project. You should first focus on getting parity with the BCC project. Make it accessible for developers first, so that it attracts a wide audience, and then think about things like performance. So
even the LLVM IR that we generate is close to O2. We modeled it on O2. So.
Hi, thanks for the nice presentation. So one question I had is, what fragment of Python you support in this translation? Do you support lambdas and?
No, so this was in one of the slides which we conveniently skipped because in the interest of time. This was the reduced grammar that we support for now. There are some changes to it that we have added support for structs as well. So if we declare a data class in Python, that can be translated to a struct. The only restrictions there are that the struct fields can only be string type or one of the integers, unsigned, signed, 32 or 64-bit. So you can make those structs. Those are converted to an LLVM IR struct type. For strings, we use pointers, and for ints or pointers, we use their respective types in LLVM IR. And apart from that, this is the grammar that we are using.
And we do plan on continuing to write more on top of this.
Essentially, you wouldn't be able to do anything that allocates on the heap, right? So, because Python runtime is not there, you can't do garbage collection and all of that. So, essentially, there is a small subset of Python here which can be converted to the underlying BPF
Yes.
representation.
And anything which is not decorated by a BPF decorator runs via a normal Python interpreter. So if it is not BPF specific, we offload it to a well-known Python interpreter.
So up next, we have team Blank Point with Edgeflow, which is a DSL for Edge AI pipelines. I also request team Captain IRS and team Q to come forward if they're here. Okay, time starts now.
We are Team Blankpoint, and we are here to introduce Edgeflow, which is a DSL that transforms the way AI models are deployed on Edge. Our goal is simple, to make the deployment as easy as writing a config file. Today, today deploying AI on Edge devices is a messy, fragmented, and error-prone process. Developers face too many problems like hardware diversity, complex model optimization, no feedback loops, and this results in misconfigurations, failures, wasted weeks, and hours of debugging. Edgeflow, this is where Edgeflow comes in. So Edgeflow provides a simple declarative DSL with a human-readable script that deploys to any device with a single config. No or minimal ML knowledge required. No PhD level knowledge required for quantization device. You just have to write a simple config file. Avoids vendor lock-ins and manual errors, and it always also leverages built-in optimizations, making the deployment universal, efficient, and reliable. So this is our declarative DSL. You can basically configure model path, framework, and target device. If you want, you could also configure the optimization settings, resource constraints, deployment configurations. So how does it actually work? So the architecture is pretty straightforward. We ingest a model, and we have a multi-format model support that supports like TensorFlow, PyTorch, and other frameworks. Parsing and validation is done. A canonical IR is generated, and then we have optimization passes. Our optimization engine runs various optimization passes like quantization, pruning, and operator fusion to generate device-specific code, which is then deployed to the edge devices. Our benchmarking and explainability module generates reports for clear and transparent reports, and then the developers could iterate through this process, making it a lot faster. What does our actually compiler do, and what are all the abstractions that our DSL provides? So our DSL provides a universal multi-framework support through canonical IR. It 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 takes inputs from various model frameworks like TensorFlow, PyTorch, ONNX, and transforms that into a single canonical intermediate representation, enabling a seamless optimization. Next, it does is like semantic validation and optimization. It catches the errors very early. For example, the mismatches in shapes or illegal configurations, and reduces the time taken for debugging errors. It is adaptive, so with minimal inputs, you could target your optimizations to the target devices without providing like specific details. What are the other core features that we have other than this? So we have automated optimization pipeline. Like I told you, just need to configure the target device and some other basic details, and other things would be automatically optimized by our DSL. Integrated benchmarking framework, which generates the reports and provides a clear detail of how throughput and latency were measured. We have hardware independent validation, so you don't need to have a particular edge device with you to test the models and run them and check its compatibility. So let's see the results now. We improve in terms of shorter deployment time. A lot of time is improved in checking the manual errors also, because we check the errors much earlier than deploying and actually running the model on edge devices. And again, the iteration cycle is done much faster because the optimization process is reduced from weeks to minutes. So what is the change and comparison with current tools? So time and complexity reduction, like I told, the tools currently take a lot of time and are fragmented. Edgeflow provides a seamless process, converting this expert tuning into 5 minutes. Then we have various vendors, but they are specific, for example, TensorRT for NVIDIA GPUs. But Edgeflow is universal. It would work from Raspberry Pi to to microcontrollers. And again, it is an intelligent and manual work, intelligent versus manual work. So the traditional way of writing, fine-tuning everything like specific details is much reduced to a simple concept file. Now, we'll be presenting the demo video.
So yeah, the story of Edgeflow starts with a really frustrated ML engineer called Madhur. Madhur is sitting in his home and he's breaking his head over trying to optimize and deploy and fine-tune his ML models. So this is where Edgeflow comes in. We start off with a really simple concept, very simple to write, and so yeah, we also have a front end for, for demonstration purposes, we made a front end. The front end, in one single click, after writing the config file, it generates codes in all languages. It performs hardware-specific optimization. It also generates and displays the benchmark results, as you can see. Yeah, the difference in time is really visible. Edgeflow also handles. Okay. So Edgeflow, while running Edgeflow, it does check your model for compatibility, and it also performs semantic validation. So this is the demonstration of when we use Edgeflow to deploy a large ResNet model on a Raspberry Pi 4. Good opportunity. Okay, no worries. Then on a closing statement, thank you all. This is Team Blank Point. Please feel to check out the platform, the front end for this. We have it on our PPT, which is right. Where is this?
We can begin with the Q&A.
Yeah, we're open to questions.
Yeah. So I have two questions for you. The first question is, you have designed a configuration file which is very nice. What guarantees do you have that you have covered all parameters that would be required? Everything that can be configured is covered. That's one question. Second question is, you talked about an IR which can cover many frameworks. So what are the main abstractions in your IR? These are the two questions that I have for you.
So the configuration, first of all, we researched and saw that there are some standardized configs that are needed, like for the edge AI deployment. So all those configs are particularly mentioned in our DSL, and like the basic configs you need to specify, like whatever your target device is, and like if you need like for some optimizations and fusion pruning. But the other things, like what the things that are device specific, we have a device profile library where we fetch all the details from. So like for most of the devices we have that, so we could fetch the details from there.
And the second one is canonical IR, which supports multiple frameworks. So we what we did was we selected the things which suppose for TensorFlow or ONNX or the PyTorch, we made separate IRs for each of them, and whichever it choose, it goes by that path. Yes. Yes.
Yeah, nice to see the project. Just want to check, did you write everything from scratch or did you use any particular tool for the DSL?
Yeah, for the DSL we are using ANTLR tool.
Antler.
Like
Oh,
yeah,
okay.
Antler for transmit.
Thank you. Next up, we have Captain IRS with DSP Lang, which is a vector processing language for high bit vectors. Team Captain IRS, please come to the stage.
Should I place it on? Do you want it to be connected?
technical difficulties, I request Team Q to come up and present. So Team Q's project is a debug dialect for MLIR. Your time starts now.
Yeah, hi all. So I'll be presenting a debug dialect for MLIR. So before going into why we need an MLIR debugging dialect. So why we need a debugging dialect for an MLIR. So whatever you see over here, so this can be considered as MLIR, valid MLIR code. So what it does is like it's basically a GEM. It's doing a general matrix multiplication. It is using affine dialect and array dialect. Some of the standard dialect that's MLIR supports. So the major issue with this IR, this intermediate level is like you won't be able to know what's inside this IR. So at the end of the day, whatever you're doing, it will be lowered it down to some LLVM at the end of the day or some other hardware specific IR. But you won't be able to see. So why this is important is like you will be writing the code to generate this code. So if you don't, so basically this is a black box. So if you don't know what's happening with this, essentially you don't need this particular capability for MLIR. But if you know, if somehow we were able to know what's happening with this percentage zero, what is this percentage one at runtime, it would be great. So if you want to know what's the value of arg0, that is all, that has it as a runtime, it would be great. Or you want to know whether your loop is running at all. So if you are accidentally accessing any out of bound memory, so all those things you won't be able to, as of now you won't be able to query all those things from this particular IR that your code generated. So why it is hard is like for MLIR. So in MLIR we have something like an operation and regions. So whatever we have is like operation, and whenever you create an operation in MLIR, you need to pass location information. That's the only debug information that the MLIR right now supports. Then that's much more than needed. That's the thing that we need right now. But with just the location, the only debug information that you will have is like whenever your pass fails, your conversion pass fails, you will get a message saying that your pass got failed due to this particular operation that was in this line number in the source code. So that's the MLIR's debugging works these days. And you can say that you can lower it entire thing down to LLVM, and then once the LLVM IR is there, you can basically debug the code. So there is also a catch, like you won't be able to debug the LLVM IR generator. Maybe you can debug the source level code, that's C or C++, or you can debug the machine level code. But in order to step through the IR, that's still not there. So that comes to the solution that we propose. So, so what we propose is, like, if you want to know what's the value of arg0, you can simply write array.print. So array is the dialect that we developed. So you just need to say that array.print, and if you want to know what's the value of array arg0, you just do this. Just like what we do with the C++ code. Whenever you have seg fault in your C program, what you first thing that you do is, like, you will just do a small printf. Or if you want to know whether your loop is running, you just want to do just like what we do with C++. You just need to print whether the thing is working or not. So for that, if you want to do some out of bound memory access, you just need to add an assert. So this is what we propose. So why this is helpful? This is damn helpful for people who write passes and conversion. So almost all the MLIR project deals with some kind of passes or conversion. So essentially, if the array dialect or this debug dialect is not there, essentially this MLIR layer itself is a black box. What our dialect does is, like, it makes this black box a glass box. And obviously, so when I started working with MLIR, so my major concern was why I can't have something like a hello world program similar to what we have in C++. So that thought, and even writing some advanced transformation or passes, what I found was, like, if we have something that can show what's our operation that we have generated can do at the runtime, then that's going to be extremely helpful. That's how we came to this project, and we have already started using this dialect in our in our projects. So maybe I'll go through a demo that will give you better understanding. Yeah, so right now we have a normal gem file that we have shown the thing. So you just need, so you want to know what is the value of maybe argument 0. So you just need to pass the save it, and so this is a very small script that will run the passes on this particular this is the input. Gem.mlir will be the input, and you can basically run the pass. As of now, it is not mainstream. When it is mainstream, you just need to add mlir opt / array convert LLVM array to LLVM or something like that. So what that pass will do is, like, it will generate one MLIR. So this will contain something like this. So basically do is, like, it will call the LLVM, the standard printf library over there. And maybe I can. So once this is done, maybe we can lower everything to the LL, so the LLVM IR. So once this is the MLIR, so we'll convert everything to LLVM IR. That's the normal MLIR pipeline we have these days. So this will generate the stop. Yeah, okay. So it will generate the LLVM. So I've written a small driver function to call the gem file. So this is the driver, and if you compile it with the generated LLVM file, so now we just need to run. So as you can see, the arg, what was that? So we printed argument 0, that was the third argument. And in the third argument, k is 1000. So this is what we have done. And there are printfs, there are asserts, and everything is there. Yeah, so that's it.
Thank you. Questions?
Yeah, do you have a list of options which you have added? Like
Yeah.
print, is that can you?
So we have added, so these were the things I could come up with, and the start time and stop time, that will basically calculate the what amount of time the operation has taken to execute. And we are still working on that. And this print shape is something I found very useful, like dynamically printing the, so memref won't have, memref will, usually memref will have a question mark and then followed by 128 or something. So at the runtime, what is the shape of the that tensor, that is a useful operation. And array dot count is there, so it will count the number of frequency of which number the operation has worked. Yeah, and those are the things we are working on, and these were the things I could come up with. So there are so many other operations that we can come up with. Anyway, it's extensible and it's open source. Everyone can contribute to this. Yeah.
Just a follow-up question on that. So have you ever thought of conditionals and adding conditionals like a debuggers?
Yeah, assert is conditional.
No, for on a value. Oh, okay.
Yeah,
From that perspective.
Yeah, yeah.
Sure.
Yeah, maybe we can think about that.
Just adding a conditional to an existing say print only when it is. Yeah.
Yeah, we can do that.
That's all.
Thank you.
Thanks.
So, next we have Nishant Sachdeva from Team Future Forge, who is presenting IR2VEC++.
Hi, good afternoon, everyone. In this presentation, I will talk about the improvements that I've been trying to make to IR2VEC and how they've come about. So what is IR2VEC? Now, as a background, compilers have a lot of optimizations, and in many of them, they use heuristics. These heuristics are often planned and made by experts in their fields, which they design very meticulously, but there is a limitation to these kind of activities. And when we use ML models to get to these heuristics, the results are often better. Now, to train ML models, you need embeddings. And how do you get embeddings? You need tools like IR2VEC, which will take LLVM IR and convert them into embeddings, which can then be used into downstream tasks. IR2VEC specifically does this by two methods. One is the symbolic embeddings, and one is the flowware embeddings. Specifically for our case today, I will focus on flowware embeddings. Flowware embeddings, the MVP here is that they take an instruction and they take surrounding context, encode them all together into one final embedding, which is supposed to be better than the usual conversions. Here, if you focus, the first two portions, the collect write definitions map and computing the reaching definitions, this is going to be the focus of my work here. Sorry, yeah, thank you. Okay, so there are a few limitations with IR2VEC as it exists right now, especially in the first two stages. Now, the collect write defs map and the reaching definitions, they use top-down DFS-like approaches to calculate the reaching definitions, which is, one, it's inefficient, has some limitations. Secondly, a lot of this is essentially re-implementing passes which exist in LLVM already. So if we can use that code, of course, model it around, make some manipulations, and then use it in actual IR2VEC, we save a lot of developer time, we make maintainability easier, and we, of course, cover some edge cases which we could have missed in our actual core code. So the MVP of my project here is that we use the LLVM API for the get underlying object, and we use the LLVM's memory SSA passes to essentially recreate the reaching definitions code that has been written from scratch for IR2VEC. Also, once this is made, once this actually goes upstream, we have also made this Python bindings package to make sure that the ML community actually can benefit from the improvements that we make. Now, RightDevs map. So, like I said, it's a top-down DFS-like approach which is in the native source code, and replacing it with underlying object API causes a massive amount of speed up, where we took a source code, we took the SQLite source code. With the original code, it took about 20 seconds to get to the RightDevs map, but with the new approach, it takes about 0.2 seconds. So that improvement is a huge plus that can go and help the community, the ML community, a lot downstream. And to test this out and to check the actual accuracy of the approach, I took a benchmark set of about 40,000 files. I ran the same approach on it, and we got an accuracy where about 99.7% test files gave back the same maps. So the good thing here we can to report here is that the LLVM underlying object API and the actual source code that IR2Vec has, they both reach the same results, but one is far faster than the other. Now, what if I told you that the RightDevs map is not required at all? This is where the reaching definitions and approach comes in. The reaching definitions take the RightDevs map, where basically for every location you have the list of instructions which write to that location. Then for a target instruction, it removes all the instructions which don't actually reach the place, hence giving us our final reaching definitions. Here, we can replace this entire process with a memory SSA API, where if we use the get clobbering memory access functions, it returns two outputs. One, if it's a memory def, that's it, answer. If it's a memory file, you take the incoming nodes and run the same process in a while loop, and then you get your answers. This is a huge simplification over what we have right now, and it gives us better results than what we have with the current IR2Vec. For example, in this case, if you see, the store instruction which takes the contents of 8 and store them to 9, the reaching definition which IR2Vec gives us is the definition of 9 as a load pointer. But with memory SSA, we reach the initial store instruction which actually wrote to that memory location. So in that way, semantically, this is a much more correct way of getting the reaching definitions. In another example, if you see here, look at the result instruction. Result is trying to load the contents of the pointer to variable. With the native IR2Vec, we get the get element pointer definition, which defines the pointer to. But with the memory SSA, we get the actual instruction, which is the store, which actually wrote to pointer to. So we have seen here that, okay, one thing to notice here is that in this entire approach with the memory SSA, there was no need to collect RightDevs map anymore. That's gone. So the speed up we got initially, even that, the whole process is simplified now. So the impact here is two parts. Here. One is that, okay, there is a performance improvement. Second, we have gotten better definitions here. This can help the community a lot, and of course, needless to say, the code becomes a lot more maintainable now. It's just one call to the memory SSA API, which itself is a battle-hardened upstream work. Now, coming to upstream. So let's say we merge this all, but then how does the community get to this? IR2Vec initially came with its own Python bindings, but that is coupled tightly with the initial native source code. So anything we put into the LLVM IR2Vec doesn't get to the Python binding. So to mitigate that, I designed is a big word, but yeah, I made a Python bindings package using this PyBind module, which is something even MLIR uses, so I took inspiration from that. We get a PyBind package, and I made the wheels files for it and put them in a Colab notebook and on test PyPy, where we can actually just one command install and run it. In fact, this is something that even the community has been asking for, so this is a issue that's been made for the LLVM project. There's a GitHub issue which asks for Python bindings for IR2Vec, so this project will also address that. But yeah, so the essential part here is that instead of using sub-process calls into LLVM to make sure that, okay, we get some bindings, we can just install and have our answer in 3 lines. So yeah, to summarize here, we have the memory SSA improvements, and we have a Python bindings package to actually support and bring that to the community. Future work we can discuss, but yeah, I would like to open it to questions.
So you talked about reaching definitions analysis. So saying you're essentially using the underlying reaching definitions analysis existing in LLVM, or have you encoded it? I got confused when you were mixing the two things. So
So One thing, reaching definitions analysis is a wrapper that we write on top of the alias analysis which already exists in LLVM, which is the native source code. Here in the improvement, in the code that I have done, it's completely calling and offloading everything to memory SSA.
No. So reaching definitions and alias analysis, what's the connection between the two?
Okay. So alias analysis, of course, will give me an API to check if any instruction clobbers the address of my instruction or not. That's
Right.
one. That is the API that the native IRTOVEC uses when it's actually checking if any instruction wrote to my instruction or not. If
Okay.
it does, then it is my reaching definition.
Oh. Oh.
All of that is already done with memory SSA.
Okay.
So my project replaces the native code that we wrote with memory SSA, where one, the maintainability of my code improves, and secondly, memory SSA covers some edge cases which I had not covered.
Okay.
Now, when I say I, it is the native IRTOVEC source code, which
Yeah. And you also talked about data. So other than reaching definitions analysis, is there any data flow analysis that you did?
No.
Okay. And this data flow analysis that you did was intra-procedural within a procedure?
memory SSA is specifically intra-procedural. I cannot go past into other functions.
Okay.
But the IRTOVEC embeddings itself, they do capture that. So let's say I have some embedding with an instruction which made a call to a different function. Now, in its own call, this function would have stored its own definitions somewhere, and then this actually brings it in to inculcate into the main procedure. But
Yeah.
in the same piece of code, no, it doesn't happen.
Yeah. Even if you did that, that will be context insensitive. If you know the distinction between context sensitivity and insensitivity. Okay.
But essentially, we cache the results for each function, and then when we realize that okay, a function call was made from function A, then we call the contents of function B and append them into our result.
Quick question. So this is improving IR2VEC,
Yes.
right? So have you considered upstreaming some of this?
Yes.
Okay.
Yeah. So like I just mentioned, the LLVM project has a GitHub issue for the Python binding, so
Okay.
that itself we can target. But of course, we'll have to calibrate our CMake files and with the standards of the LLVM. But in general as well, one is that I want to make sure that the approach is correct. There are some cases in memory SSA as well, where let's say if it reaches a memory 5. Now with a memory 5, it tries to get all the incoming nodes and tries to run some optimizations on it. There are some cases where it will return only one dominating instruction. Now I don't always want that. I want all the live definitions which reach my instruction. So there are some cases where I would want to have some control. So those things, trade-offs, we'll have to decide on. And then yes, target is to reach upstream.
Okay, so you don't have to replace it, right? You can add it as an additional sort of
course,
analysis
yes.
where this would be useful.
Yes, yeah, that would be an engineering work we can see, because IR2VEC, like I said, it collects write defs map and some initial information before it begins its work. So if I am going to allow for memory SSA, then none of that is required. But that's an engineering work, but yes, we can have a flag where users can decide which one they want to use.
So you have not considered upstreaming yet, right? So
No,
that's
this
what
is, I would still say this is something in progress. I want to have a more sturdy results before I go ahead.
Yeah, we'll stop now in the interest of time. Up next, we have team Ubiquitous with their LLVM powered deobfuscator.
Yes, thank you everyone.
This is the second last presentation. Your time starts now.
Okay, so good evening, everybody. I'm Ketan, and I'm here to present Ubiquitous, which is an LLVM-powered program analysis tool for breaking binary obfuscation. Quickly, let's discuss what is obfuscation. Obfuscation is writing bad code, but intentionally, as opposed to the common folly of unintentionally. Why would somebody want to write bad code intentionally so that it becomes hard to analyze? What is the common use cases in malware? Malware authors don't usually want their code to be reverse engineered and analyzed, because that would obviously hinder the malicious activities. Other people who want to do this are people who want to implement and protect their IP. So there's a lot of DRM systems who obfuscate their code, and you don't want other people to poke into your code and find out your algorithms and reverse engineer them. So people tend to obfuscate code.
What have we built? We've built Ubiquitous. So we're showing that obfuscation is barely secure, and we do this by breaking obfuscation. And we do this by breaking obfuscation by commercial tools. It's not our own tool. These are commercial tools that are used by many people. So let's discuss core components. We've written our own LLVM interpreter for this purpose. We've not used LLI because I didn't like the code base, and I found it hard to hook into it. So I've written my own LLVM interpreter I support about 30 or so opcodes. We support about 30 or more opcodes, and we're in the process of extending this. We've written a taint tracking engine, a control flow recovery algorithm, and opaque predicates optimization. More on this later. This is our CLI, quick look. Let's talk about targeted deobfuscation first. This is a weaker algorithm of deobfuscation wherein you target it to particular obfuscation algorithms. So this is control flow flattening. This is not how a regular program should ever look like. There is no hierarchy between if and else. Everything is flattened. But typically, you would have an if-else construct, and the program follows a nice, clean flow. But if you flatten it using an obfuscation tool, this is done by Tigris. It's a very popular obfuscation tool written by University of Arizona, I think. I'm not sure. But this has been flattened by Tigris, and a lot of other obfuscators produce similar code. This is how we unflatten it. So we do a dominance analysis to first detect loops. After performing a dominance analysis to detect loop, we implement heuristics to detect this dispatch block. So you can see the main block that dispatches to every other block, the one with the fewer instructions, and it leads to every other block. So that's the dispatch block. Once we have identified dispatch block using our heuristics post-dominance analysis, we can walk through the flow and reconstruct this. So this obfuscation can easily be broken. Let's talk about some metrics. We can see that we've reduced branches by a significant amount. Let's talk about opaque predicates. What are opaque predicates? Opaque predicates are conditions which seem to be conditions, but when you actually look into them, they're either always true or always false. So it's either like if 1, while 1, or while 0. But when you do static analysis, it seems to be a complicated condition. So a simple example would be if x squared greater than 0. We know if x is an integer, it's always going to be greater than 0. It's always going to be positive, I mean. So that seems like a condition. So you get 2 branches, but one of them is always unreachable. So in static analysis, the control flow graph looks really, really long and weird. But upon symbolic execution, we can just resolve and prove that most of those conditions are either 1 or 0. I'd be happy to discuss the exact algorithm for symbolic execution in the Q&A session. But there are certain limitations of targeted deobfuscation. What are the limitations? It is not a general solution. It depends highly on heuristics and the implementation of the obfuscation. So if the obfuscation designer makes a few changes, our obfuscation is suddenly no longer valid, because we relied on certain heuristics to deobfuscate. Also, opaque predicates, we also have a certain kind of obfuscation called virtualization of code. Now, this is one of the most powerful obfuscations, and it's heavily resistant to static analysis. How does that work? Okay, so this is how virtualized functions look like. Now, this might look similar to a control flow flattening algorithm, but it is not. The dispatcher there is an interpreter on its own. What I mean by that is the program itself has been transformed into an interpreter. So the interpreter is going to have a custom bytecode. Let's say bytecode 1 represents the AND operation, bytecode 2 represents the OR operation, and all these operations are implemented in bytecode. So the bytecode is stored somewhere in the global memory. There'll be a program counter, there'll be a stack, there might be a heap. There's this unlimited kinds of VM design that you can go through. The problem with this is now obfuscation designers have a lot of freedom in what kind of VM they want to design. So there is no fixed heuristic that we can go with. It can be a heap VM, it can be a stack-based VM. The bytecode can be in global memory, can be locally. So it's basically the point is static analysis cannot do this. How do we fix this? Taint engine. So what is taint analysis? Taint analysis quite simply is when you taint a value and then you track how the value flows through the program. So what we do is we taint the input of the program. And as operations are performed on the input, we track what are the exact operations that the input is going through. So this is called dynamic taint analysis, and this is what I wrote my interpreter for, so that I could execute the LLVM IR and track exactly what is happening to my input. Now there's 2 kinds of things that happens here. We need to record all tainted instructions, because this will give us something called data dependency. So if I have my input, which I taint by default, and then I have something called result is equal to input into 2. So now the result is a data that is dependent on input. Computation on input gives me result. So this is called a data dependency, so result will also become tainted. Now if the input is stored to a memory location, that memory location is also going to be tainted. So we have certain taint propagation rules. I'll be happy to discuss what the rules are for taint propagation. We also need to untaint memory to prevent over-tainting. If you have over-tainting, then you virtually have a big trace, and that is as bad as obfuscated code. So I'll be happy to discuss the exact algorithm. We also log all the VM instructions. By VM, I mean the interpreter, virtual machine. We also log that. Why do we do that? Because, like I mentioned, there's a data dependency, and there is something called a control flow dependency. So if you have something like if input equal to 0, y equal to 10. Now, y does not directly depend on a computation on the input, right? It does not say y equal to input into 2. What is happening here is it's a control flow dependency. If input equal to 0, y equal to 10. To do this, we need something, we will have to combine post-dominance analysis along with our tainted instructions to finally retrieve this code. So you can see that, again, we went from this virtualized function. After taint analysis plus post-dominance analysis plus running the O2 pass of LLVM, we came to a simple hash-like function. This is the sort of function that you would like to hide in a VM because it's very easy to analyze, but it's also crucial because a lot of license checks, a lot of malware stuff use this kind of functions. But I'd be happy to discuss the algorithm more in detail. Yeah, thank you. I'd like to invite my teammates also on for the Q&A round.
Question.
Some metrics and some limitations. Okay.
So I have two questions. So basically, first is you have a closed world assumption about the obfuscation. So you're assuming that obfuscation is only of these 1, 2, 3, 4, 10, whatever n number of ways in which it can be done. Is that right? Or
for the first 3 obfuscations, yes, which was control flow flattening. No, for the first 2 opaque predicates, yes. But the taint engine does not assume anything. I was only showing virtualization because it is the most powerful kind of obfuscation there is. So if the taint engine can work towards that, it will also work towards control flow flattening, for example. Suppose you don't want to rely on heuristics to do control flow unflattening. You can use our taint engine because it's also going to track the taint and it will produce a neater CFG. So we are not making assumptions, but yes, there are definitely some types that we cannot handle.
So what you're calling as taint engine, to me it looks more like slicing.
Definitely, yeah. I am not exactly 100% up to date with the definition of slicing, but yes, taint engine I read in a paper somewhere is similar to slicing.
Yeah. So that second thing, you're doing it dynamically. You're not doing it statically, which means that you're not sure that you have covered everything.
Oh, exactly. So if you look at further work here, we want to implement a symbolic state tracking. We have already started doing that. Yeah. This will help us incrementally track paths. So what we're doing is once we come to a condition which is tainted, so that condition depends on the input. There's obviously going to be a few paths, and we can only take one. But we will track the symbolic, the operations performed on this input up to this point, so that we can feed it to a SMT solver, Z3 for example, and generate a new input, and we will run the program with the new input to explore the other paths. Now the user will give user freedom to see how many paths they want to explore, because there might be path explosion if you set all the paths. There might be path explosion.
Why not static analysis?
A static analysis for VM we found to be very, very inefficient because the VM might be loading bytecode from. The problem is you'll have to do all sorts of analysis. You'll have to do pointer analysis, alias analysis, and this is going to be a big, hard problem, and it might not even be very accurate. So yeah. But we are relying on static analysis, which is post-dominance analysis, to complement it with our taint engine.
Thank you. For our last team for today, we have Captain IRS with DSP Lang.
I'll be talking about the DSP Lang project. Uh, so let's start with the motivation. Like when you're writing code targeting like vector processors, like you either like you have this trade-off of like control over performance versus the ease of programming. So I wanted to create a language that sits right in the middle, like between the intrinsics and writing using some vendor-specific SDKs. So it's essentially a language that gives you constructs to build something like a MATML kernel. So the goal is to like develop a vector processing DSL for architecture specifically like NPUs with high bit width vectors, and ideally I should be using MLIR to progressively lower the DSL. And I specifically focus on the Qualcomm Hexagon NPU for this. So NPU usage is on the rise, like with ML image processing, vector processing workloads. So the problem is like LLVM doesn't like utilize these like max bit width effectively. So you should be writing like code in like backend specific intrinsics, which is very painful to write. So we need something better than that. So that's the motivation behind this project. And specifically with respect to the Hexagon NPU, if you see on the left, like this, the code here, like it uses the scalar processor. It doesn't use the vector processor in the NPU SoC. So we need to change this. And this was like just 3 days before I submitted this, and like even Qualcomm seems to be thinking in this direction, and they have this new RFC to LLVM related to this specific problem. So the hardware target is the Qualcomm Hexagon NPU, and this NPU has this HVX unit, the Hexagon Vector Extensions, which I'll be leveraging in this project. And unfortunately, I couldn't show a live demo. I could have shown it in this phone, which I have, but unfortunately, I couldn't get the laptop working with this, so sorry for that. So I'll skip the aspects of the hardware since it was covered by a Qualcomm talk before this as well. So the high-level architecture here is that like the DSP Lang and the DSP Lang dialect are derived from the MLIR toy example, which is given by the LLVM project itself. And it leverages a lot of the existing infrastructure like the ARIC dialect, Affine dialect, and vector dialect. And the main contributions of this project are these two new dialects, the HLHVX dialect and the LLHVX dialect, which eventually help you to lower any dialect to this LLVM IR. So the more about the dialects, the LLHVX dialect is a direct interface between MLIR and LLVM IR. Currently the Hexagon intrinsics are not exposed to MLIR. So this is the first project, the first open source project to do this. And the problem with the low-level dialect is that the type information is not there. There is no specific type information. So I have built a high-level dialect which has the correct type information, and we progressively lower it from the high-level dialect. And this is how the DSP Lang dialect looks like, and it operates on like tensor and member of types. And this is the key contribution of this project, like the selective vectorization pass, where it analyzes the loop body for the data types which are being used in the loop and determines the step for the loop to do the vectorization. So the front end is basically like modified from the MLIR toy example. So Johnny, let's walk through the passes quickly. And the DSP Lang dialect, like the traditional LLVM passes are applied to it. And this selective vectorized pass basically like determines the step size as 32 and does the vectorization. And then it's converted to HLHVX, and this is converted to LLHVX, and then to the LLVM dialect and to LLVM IR. And when the optimizer is done, like we'll be able to generate the vector processing code, the most efficient vector processing code for this particular use case. And since we don't have the demo, I just have some screenshots, and we have this DSP Lang implementation and the C implementation. The DSP Lang implementation effectively uses the HVX vectors, so it's able to get some performance improvement at the cost of a loss of precision. So these are the like HLHVX and LLHVX ops written using TableGen. and the translation test suite is also like auto-generated. And for converting from HLHVX to LLHVX, I experimentally used the PDLL instead of using TableGen. And Arith to HLHVX is also lowered using PDLL. So this is one of the first dialects in existence to basically like expose these HVX intrinsics to the broader ML layer ecosystem, and it's open source as well. It's like end-to-end fully open source and reproducible. And the future work is currently like only binary operations are supported. In the future, like reduction-based workflows like and sliding window-based workflow will also be supported. So thank you.
Questions?
Yeah, can you just go back to the code that you were showing? Not this, before that. Not the implementation. Yeah. Okay, so affine passes, you are not generating this, right?
These are like used from LLVM directly.
These are
Yeah.
LLVM dialect, right? So the step that you are getting, can you go to the part where you were seeing the step?
Yeah.
Step equal to 32. Yeah. So this is generated by LLVM. Sorry,
This
MLIR, right?
this
The
step is
affine
determined
pass.
by me. Like
This is generated by you?
yeah.
Okay, so how
This
do you
pass.
determine this?
So I basically look at the like loop body and see the data types it's operating on.
Okay.
In this case, like all the operations are happening on F32. So the target bit width is 1024. So I just divide 1024 by 32 and determine the step size for this particular instance.
Okay.
Okay, thank you.
Yes, so that brings this session to a close. Up next, we have a talk from CDAC about compilers in CDAC by Ms. Prachi Pandey. Meanwhile, I request the judges that if they want to discuss the results and evaluation, they can move out to the right or left.
Just a minute, let me check. Where is it? Just pinch it. It's coming? Yeah. This works? Good afternoon, everyone. For those of you who are still awake and still present. So I'm Prachi Pandey, and I'll be speaking about the compiler research and development initiatives at CDAC Bangalore. But before I begin the talk, I would like to thank the IICT organizers for bringing this platform, bringing all the compiler enthusiasts under one roof. And that's a tremendous work done by them. And also congratulations to the hackathon finalists all of them have done a very commendable job. Wish them all the best. I know you must be nervous about the results, so wish you all the best. So I'll be discussing about these things, just an overview about CDAC and its journey, then about one of our products, CAPSI, which is an automatic parallelizing compiler, and our open source SYCL compiler initiative from CDAC, which is called as PARAS. Then I'll be telling about the CDAC indigenous processor roadmap, and finally about our indigenous compilers which are targeted for these CDAC processors. And I would also in the end like to discuss the career opportunities in CDAC for compiler developers. So CDAC, which is the Center for Development of Advanced Computing, is the premier R&D organization of the Ministry of Electronics and Information Technology. It was started with a bold mission to develop supercomputing capability in India. In fact, it's a very interesting story. I encourage all of you to look. It is there in the internet how CDAC was founded. So you can go back and look it up. And we are the pioneers of Param supercomputers, the first one to bring supercomputing in India. I think I have a next slide which talks about that. But now we are into all other verticals as well, other than HPC. We are into quantum computing, we are into artificial intelligence, the DER5 program, then we are into eGov projects, IoT, VLSI, and so on. So this is the CDAC Param series of supercomputers that I was talking about. The first one, Param 8000, was in 1991, and this was a result of technological sanctions imposed on us, which is the story I was talking about. And something makes me feel that we are heading that way again. But yeah, that was a result of the impositions on India for import of supercomputers. Then from Param 8000 to 10,000 to Param Padma, which was the first supercomputer to feature in the top 500 list of supercomputers in the world. And then we have Param Yuva, which was also there in the list. The Param Shivai is in IIT BHU. There's Param Shakti in IIT Kharagpur. There's Param Porul in NIT Trichy, and all the major institutes in India. We have our installation. Even here in IAC, we have Param Pravega, which is a 3.3 petaflop system. And now we are also releasing in a few months the biggest supercomputer of India in CDAC Bangalore, which will be of the capacity of 30 to 50 petaflops. It will be soon getting released. So like I was saying, we have an automatic parallelizing compiler. You would have seen the poster in the poster session. So I'll just tell an overview about this. This takes a sequential program as input. The typical HPC codes, sequential codes, C, C++, Fortran codes, and it converts automatically to parallel codes in OpenMP, OpenACT, and OpenCL. And behind the scenes, it has typical compiler technologies, which we are employing here, which is liveness analysis and dependency analysis, your control flow analysis, and so on. Then we manipulate the AST to finally get the parallel code. And this is also deployed on all the Param supercomputers that I was mentioning about in the previous slide. So the next one is the open source compiler initiative from CDAC, which is PARAS compiler. The theme is code once, execute for all, which means that you write a code once and the same code will execute in your CPU, in any variant of GPU, be it AMD, be it NVIDIA, or anything. So this basically gives the user the flexibility to just write a single source code and it can execute on any target. Again, this is available in GitHub actually. You can see the link over here and also the QR code. So I encourage you all to use it, to explore it, and also to contribute to it. There's a huge growing community of SYCL, so you can explore that as well. Currently, it is tested on all the popular CPUs like Intel, AMD, NVIDIA, and the GPUs like AMD and NVIDIA as well. And it is available on Indian supercomputers and multiple international installations. So you could contribute to the community. Now coming to India's indigenous processor roadmap. So this is with the ambition of achieving self-reliance in technology. So with that goal, we are coming up with the line of processors both for embedded class as well as HPC class. The first one, Vega processors, Vega series of processors, is already available. It is for the embedded class, and it is available in 32 and 64-bit form. It is there in single and multi-core version as well. Then coming to the HPC class of processors, the immediate one that we have coming up is OHM processor, which is based on ARM Neoverse V2 architecture. So we are developing a processor based on the ARM architecture. And also, we have started the development of HPC class CPU based on RISC-V architecture. The OHM processor is slated to be released in 2027, and the RISC-V based HPC core CPU architecture is slated to be released in somewhere around 2029. Along with the CPUs, HPC CPUs, we are also having a plan for release of our own indigenous GPGPUs as well as AI accelerator. So the GPGPU is based on RISC-V architecture with our custom instructions, and it supports both matrix cores and HPC cores. And our AI accelerator is based on systolic array architecture. It is having a proprietary ISA, and it supports both AI inferencing and training. So this is basically about our roadmap for achieving total sovereignty for processor technology in India. So next, this is about, your processors alone cannot give you self-reliance, right? The hardware alone cannot do that. There's a need of software which will drive that innovation. So we have our own indigenous compiler developed in CDAC, which is for powering these indigenous processors, which are again developed in-house in CDAC. And that is called as Chakra. So in fact, I'm introducing Chakra in this forum, which is our indigenous compiler from CDAC. So it targets all the indigenous processors that I was talking about, including the compiler for OHM processor, Chakra for RISC-V based CPU processor, then your Chakra for GPGPU, as well as Chakra for AI accelerator. So we'll see each of this one by one. The Chakra for OHM processor is based on the LLVM framework. Like I was telling, the processor itself is based on ARM Neoverse V2 architecture. So we have taken the LLVM toolchain for ARC64, and we are optimizing that toolchain. We are currently targeted some platform independent optimizations in the mid-end, which is for HPC class of applications. So like vectorization, we have changed the default vectorizer of LLVM with vPlan, and it is giving us some promising results. We have also done some loop optimizations, like loop interchange, loop unroll and all, which also have been posted to the open source LLVM community. This we are doing along with, we are syncing up with the ARM compiler team for coming up with these. And we are also targeting hardware-specific optimization for our own processor. So both of this will be benchmarked with the HPC workload, because this is targeted to be a HPC class processor. Then we have the RISC-V class of HPC processor, Vishwa AP, which we are going to call. So the Chakra compiler for that is again based on LLVM framework. But right now what we are planning to do is make the ecosystem of LLVM strong for RISC-V, especially for the HPC scenario, because the LLVM toolchain for RISC-V right now is in a very nascent stage when it comes to HPC. The x86 and the ARM ecosystem is still evolved, but we are interacting with we are collaborating or contributing to the open source community, where we want to make it more robust, more stable for the HPC class as well. So the same kind of optimizations that I was talking about, mainly targeting vectorization, loop-based optimizations is what we have started with. Then coming to Chakra compiler for Vishwa GPGPU. Now this is again India's first GPGPU that we are planning to, that we had already developed. The prototype has been done on FPGA. And for the same, we are developing the Chakra compiler. This is based on, again, on the LLVM framework. And it will support both matrix cores as well as HPC cores. And we also have toolchain support for POSIT number system, which is an alternate number system to traditional floating point number system, which gives better accuracy in certain AI workload cases. So we are also targeting that. And the main thing why we are so confident that this program will be a success, because everything is done in-house. From the hardware team, which is doing the GPU development, to the compiler team, to the device driver team, runtime team, the software stack, everything is in-house. And so this will lead to seamless integration with all the components and better optimization. So coming to the compiler-specific backend development that we are doing currently for GPU, there were talks from yesterday, like what are the key things that differentiates between a CPU and GPU. The memory access being one significant thing, right? So we are also doing that. For memory access, we are doing the optimizations. And then also, since we have taken the base RISC-V ISA, which is essentially scalar instructions, so we have to add our own custom instruction support for SIMT operations. So for threading and for generating the sequence of instruction which would work in a SIMT fashion, we are changing the LLVM backend for that. And also for matrix core support, we have added our instruction. For memory operations, we have added new instructions. So basically, it's a combination of RISC-V ISA plus our own custom instructions. And it has to be compatible with the popular AI frameworks as well as your HPC programming models for GPU, like OpenCL CUDA. Next, we have the compiler for AI accelerator. Like I said, it would support both inference and training, and also, again, it would support POSIT number system, and it will be both AOT and JIT compilation as the need is. It is MLIR-based design, and we have developed some dialects, some custom dialects for CDAC for targeting our accelerator. It has, which includes quantization, sparsity, etc. And then many graph level optimizations have been done. For example, graph fusion, layer fusion, operator fusion, and so on. We'll also, same for GPU and AI accelerator, we are planning to have a system built for that. So we have multi-accelerator support, which supports distributed training. In the same way for GPU, we are having multi-GPU support. And then implementing of optimized memory strategies. So all of this together makes our MLIR-based compiler, Chakra compiler for Vishwa AI accelerator. So that's about our compiler initiatives that we are working on in CDAC. Now, this is something I would like to stress for you people. If you're interested to contribute in any of those areas, there are many ways you could join CDAC. For students, we have internship opportunities, both for BTech final year, which is 6 months internship, and the MTech students, you have 1 year internship opportunity in CDAC. So if you're within the top 50 NIRF, there's immediate internship options available. And upon successful completion of internship, you'll be mapped to the CDAC roles. Then for graduates also, we have currently openings going on. We are planning to start, in fact, our campus recruitment in all the leading colleges in India. And parallelly, we also have an open ad. Also, we posted in the job portal itself. We have a QR code where you could register. You don't need to register. You just need to send a couple of details, fill in a couple of details, and we'll be reaching out to you with whatever you want to work with us. So with that, I would end my talk. Thank you. Any questions? Thank you.
So we have a quick conclusion ceremony. Just a minute, yeah. begin the conclusion and award ceremony for the Innovations in Compiler Technology Conference 2025. So first, a few short notes. In numbers, this year's conference saw 379 attendees with 312 male participants, 67 female participants, 248 professionals and 131 students. So this is up from the 210 participants that we had last year in total. In addition to this, the SegFault Hackathon in its initial preliminary rounds had 48 teams with 101 participants. So all in all, this conference workshop reached about 500 people. Some other numbers, the youngest attendee is about 19 years old. Actually, there's a bunch of 19-year-olds. The oldest attendees are over 60 years old. The average age of all the volunteers is 20 years old. All of them are second year and third year BTech students that ran this entire conference. We had 21 talks, including 3 invited keynotes, 6 hackathon presentations, 10 poster presentations across 2 days. No wonder all of us look really tired. It's been a pretty intense 2-day program. We had wide representation across a lot of companies. Here are some of the companies that were represented at the hackathon. This is a very small sample. We had NVIDIA, engineers from NVIDIA, Intel, AMD, Cerebras, Broadcom, Blackfig, Google, TCS Research, MIPS, Amazon, CDAC, Sony, Multicoreware. And on the academic side, we had good representation from a number of colleges. We had students and faculty from IIT Bombay, IIT Madras, IISc Bangalore, IIT Hyderabad, IIT Delhi, PICT, Dayanand Sagar, PES, KTU, VIT, KLE Tech. Also, this is not a one-time thing that compiler engineers don't need to gather once a year or twice a year. LLVM Social Bangalore runs monthly meetups. We have over 3,000 members. That makes us the largest compiler gathering in the world. So we have a YouTube channel where all the talks from this conference will be posted. You can find it on YouTube at LLVM Social Bangalore. You can also subscribe to our meetup page, so if we're ever meeting up either here in IISc or in one of the tech offices, you can meet us there. And this is the committee. We had a wide variety of support from almost all of the leading compiler practitioners and the organizing committee. And the volunteers were from Point Blank. If you saw them in their hoodies and jackets. So it's a student team based out of Dayanand Sagar that competes in competitions, does open source, does hackathons, organizes competitions and everything else. If you're looking to hire bright engineers, look up at careers.pointblank.club. This is a photo of the volunteers. And a big thank you to our sponsors from NVIDIA, Google, Qualcomm, Quadric. Also thanking our knowledge partner CDAC for sponsoring this hackathon. A big thank you to Point Blank and ACM and iSoft for supporting this conference and the workshop throughout. So first off, I'd like to call all the judges on the stage for a small token of appreciation.
Mr. Hari Babu from CDAC, could you please come? Yeah. I have been given the responsibility of announcing the names of the hackathon winners, and it's a pleasure for me to announce them. They will be given prize by Mr. Hari Babu from CDAC. So the third prize goes to Team Future Forge. Team Future Forge, please come here. Please come quick. Be quick. You're getting a prize. The second prize goes to me because I don't know LLVM. And the first prize, any guesses? The first prize goes to Team Ubiquitous. I would like to call the remaining teams on the stage for their being given some mementos for participation. Please come. I don't have the names here on paper, but please, on the remaining 3 teams, please come on the stage. And now there are certificates for all the 6 teams. Please come on the stage. Certificates from CDAC.
So teams, we don't know LLVM, Ubiquitous, Captain IRS, Team Q, Blank Point, all of you please come on stage, Future Forge.